Let's dive into chapter number 3, contents, methods of analysis, so mesh and node analysis. And the learning objectives for this chapter are laid out here. And we're going to focus, instead of PaySpice, we're going to focus on the examples using MATLAB and MathCAD. So the outline is the following. We have in a small brief introduction, then we go over node analysis, the concept of Supernode, mesh analysis, Supermesh, and then a little bit of a linear algebra review, which are concepts that are important that will help us analyze our circuits. Let's go over the introduction, and so far you're familiar with Ohm's law, Kirchhoff's laws, KCL and KVL, equivalent resistance, circuit reduction, and power. The new tools that we're going to learn, they just build up on top of the tools that you already know. So let's go over nodal analysis, which is also known as node voltage method. And all we are going to do is to follow a set of steps. So the first step for node voltage method is you're going to select a node as the reference node, and we're going to call that the ground. There are different symbols to represent the ground. In our examples, we're going to use this symbol. Every time that you see this symbol connected to a node, you already know that that's your reference node. After that, you assign voltages, V1, V2, Vn minus 1 to the remaining nodes. All right, so let's see an example. Let's say we have this circuit, and step number 1 is let's find all the nodes. So we have been doing this. We have a node here, another node there, and another node there. The second step is, it's still step 1, but the second part of this is now to find one of these nodes as your reference node. And you can pick anyone and solve it. Just have in mind that you're going to get different answers if your reference node is in a different node. We're going to, for this particular example, select the ground or reference node on this node here on the bottom. After that, we're going to label all the other nodes with either V1, V2, VA, or VB. You pick. As long as you are consistent, that's what it matters. So we have node VA and node VB. We now move to step number 2 of node analysis, and now we apply KCL to each of the nodes that it's not a reference node, and then we're going to use also Ohm's law to express the branch currents in terms of node voltages. So let's see that in action. We go back to our circuit. We have the nodes that we identify from step 1 plus the reference node, and I'm going to assign some currents because I need to apply KCL. All right, so regarding the currents, so notice that this is a current source, so I don't need to do anything. This is already a current source, I don't need to do anything. For the other ones, assign a current with any direction that you want. As long as you are consistent when you apply KVL and KCL in Ohm's law, you're going to get exactly the same answer. Meaning, if I go here and instead of doing I2 in this direction, if I pick another direction, even if I have the plus and the minus like this, as I go and extract the formulas out of the equation, you should get exactly the same answer. All right, so I assign random directions, and I'm pretty consistent. I normally, if I don't have the plus and the minus in the circuit, I tend to use the plus and the minus with the direction of your arrow. And now let's apply KCL on the nodes that are not a reference nodes. So for the first one, we see that the sum of the currents going in needs to be equal to the sum of the currents going out. So 10 amps is entering the node, and then all the other ones are leaving, I1, I2, and 5 amps. You apply exactly the same thing at node VB, and now you have 5 amps entering, I2 is entering, and I3 is leaving. Now we're going to apply Ohm's law on these currents, I1 and I2 and I3. And if I apply Ohm's law on I1, I'm going to have the voltage V1 divided by 6, I2 is the voltage V2 divided by 4, and I3 is the voltage V3 divided by 2. And notice that I'm writing these in steps, because now we're going to write V1, V2, and V3 in terms of the node voltages that we labeled. All right, so let's do that. So if you pay attention here, now we'll apply Ohm's law. V1, which is the voltage across the 6 ohms, is VA minus 0. V2 is going to be VA minus VB, and V3 is going to be VB minus 0. All right, so if I pick up now these equations, and I plug them back into my KCL and KVL. Notice that I go from a 2 equation with 3 unknowns with a 2 equation with 2 unknowns of VA and VB. So substituting that on the equation, you massage that equation and you get something like in this form. All right, now you have your set of equations, and we go back to our step number 3, which now we need to solve these simultaneous equations to obtain the known node voltages. All right, so notice here that I have my VA and my VB, so 2 equations and 2 unknowns. This is what it's called a system of linear equations. Linear because VAs and VBs, these are all part of one. And then we have constants over here, and we need to solve these. And to solve these, there are different ways of different techniques that you can apply. For circuits 1, we are interested, or it's convenient and faster if you use the matrix inversion or Cramer's rule. So both these techniques should give you exactly the same answer. And for this particular exercise, if we do that, you get a VA of 20 volts and a VB of 13.33 volts. All right, so we're going to proceed with some practice problems where I'm going to apply some of these matrix inversions and Cramer's rule. But for more details, there is another video that I go over linear algebra review, and I go into more detail into this matrix inversion and Cramer's rule. All right, so let's go over the first practice problem, which we have this circuit over here, and it's asking to obtain the node voltages in this circuit. So notice that this exercise is already giving you step number 1 done. It's already giving a ground reference node, or a reference node, a ground, and it's giving you V1 and V2, or node 1, node 2. So all we need to do is to do step 2 and step number 3. So let's go over that. All right, so one of the things that I like to do is to design the circuit, and sometimes I even redesign the circuit accordingly to any needs that I have, so I can visualize the components in a way that I'm familiar with. And I also try, as I'm redesigning the circuit, I try to put as much information as I can on the circuit. So let's just put all that information here. So we already have a reference, a ground, and this is our 14 amps with our 7 amps. I'm going to write those resistors, 4, 5, 5. Oops, sorry about that. And let's write the nodes that I know. So V1 and V2 are given on the exercise. So all we need to do is to go directly to step number 2. And step number 2 relies on doing the KCL on those nodes. So I'm going to assign some currents, again, randomly assign those plus and minus with I1 and I2. You don't need to overthink here. It will always be correct as long as you're consistent in your analysis. And let's take KCL at node V1. All right, so if we do that, we see that we have 14 amps going in and I1 and I2 are going out. Now I apply Ohm's law on those currents, so I get V1 over 4 plus V1 minus V2 over 5. And I'm going also at the same time apply KCL at node V2. And on this one we have I2 entering the node and I3 and 7 amps exiting the node. Let's apply Ohm's law and you get V1 minus V2 over 5. And my I3 is it's V2 minus 0 divided by 5 plus 7. All right, so one of the things that I recommend doing is reducing, I normally multiply by the highest denominator. In this case is 5. It just makes sure that it just makes my equations a little bit easier. As soon as I can, I just try to do that. Just do a couple of math here so we can add things together. So you get 2.25 V1 minus V2 equals to 70. And I'm going to do the same thing on this side of the branch. So multiply everything by 5. So notice on our equation become super easy to manipulate. And pass the V2 to the other side of the equation. Now I have two equations with two unknowns, and I'm highlighting here so we know which equations we are talking about. Now let's write the matrix, those equations in a matrix form. All right, so my A is going to be my coefficients of my variables, so 2.25 and minus 1. Oops, here should be 1 and minus 2. And then my B is going to be the constants that are not related with your variables, so 70 and 35. And I'm going to apply matrix inversion, and that's just because it's very easy to do that in a calculator if you can. And matrix inversion just states that you do the inverse of your matrix A times your B. All right, so let's just pick up the calculator and let's just put that information inside. So my A is there, creating a matrix 2 by 2. Fix that, okay, and I have 2.25 minus 1, 1, and minus 2. All right, now I'm going over my matrix B. It's also it's a 2 by 1, and I have 70 and 35. All right, so now I have matrix operations, so I can just do the inverse of my A and multiply that by my B and get the answer of 30 minus 2.5. So remember that X, the first element, so the first row and column, is related with V1. So V1 is equal to 30 volts. And the other one is V2, which is minus 2.5 volts. All right, so now let's go over another exercise. And this one is now, it's going to have a dependent current source. So the current that this dependent source is providing depends on the current I of X. So let's see how to apply node analysis in this circuit. All right, as usual, I'm going to redesign my circuit over here. And I will try to also write as much information as I can in my circuit. So what you can do as you watch this video, you can try to solve it by yourself. Either stop the video or solve it at the same time. And in this particular case, it's also given the reference node, so our life is made easier. So I don't need to do step 1. I can go directly to step 2 of node analysis. Write that information here, my resistors. All right. And just write that IOX also here. All right, so we start with step number 2. In step number 2, so we need those currents, assign those currents. Let me just put the voltages because they're also given on the exercise. So we have V1, V2, and V3. All right, let's assign currents. Again, play around with it. Don't overthink, just assign random directions. I highly encourage you guys to repeat the exercise with different directions on current and see if you can get the same answer, just to validate that. All right, so let's apply KCL at V1. And if I do that, I get 4 amps are going in and I1 and I2 are going out. Apply Ohm's law. V1 minus V2 over 3 plus V1 minus V3 over my 2 ohms. All right, I'm going to apply KCL at V2 and apply the same thing. So now I have I1 and 4IX coming in and have IX going out. So this one is pretty straightforward. Just pass the I-axis together, equals to 0, and apply Ohm's law on that I1. And actually I know Ix, and it's something that if you can just put it. So I'm going to put here V2 over 4, and I'm just going to write that expression. I should have written at the beginning because it helps as you write your equations. All right, now let's go over our third expression or third equation, and from here we have I2 equals to your 4ix plus I3. Apply Ohm's law. So again, just be consistent with all these rules and you get the same answers. All right, so 4ix is V2 and I3 is V3 over 6. All right, so we have three equations. Now we can start I'm going to simplify these, multiply everything by 3. And if I do that, it will make my math a little bit easier. All right, let's just put all those terms together. Just add a couple of things here really quick, making sure that we're going in the right direction. And we get 2.5 V1 minus V2 minus 1.5 V3. And this is equal to 12. And apply exactly the same thing on this side, multiplying everything by 4. All right, put those V2s together. I get 5 over 3. And then over here, same thing. I'm going to multiply everything by 6. And that's just a rule of thumb that I do on these. You don't need to do this. You can just keep going and work with fractions if you want. I just found it easier to do this. Normally it simplifies the equations and reduces the chances of making mistakes on those equations. I'm going to highlight the 3 linear equations that we have. So we have one from KCL at V1, another one from KCL at V2, and the other one from KCL at V3. All right, let's apply now step number 3. Let's write the matrices. So A is equal to 2.5 minus 1 minus 1.5, or minus 3 over 2. And then we have 4 thirds, 5 thirds, and 0 for V3. And then we have 3 minus 6 and minus 4. All right, this is my matrix A. And your matrix B is going to be the constants that are not attached to variables. So 12, 0, and 0. And let's find X. It's going to be V1, V2, and V3. And find some space, put it here on the bottom. We're just going to I'm going to apply the matrix inversion. So find the inverse of -1 multiplied by B. So once again, I'm going to put that into my calculator. All right, so it's a 3 by 3, 2.5 minus 1 minus 1.5, 4 divided by 3, 0, 3 minus 6 minus 4. All right, let's do also matrix B, which is a 3 by 1 with 12, 0, 0, 0. All right, cool. So too fast here. Let's get the inverse of our matrix A multiplied by B, and you get the answer of 32. So V1 is equal to 32 volts, V2 minus 25.6, and V3 62.4 volts. right, so we don't need the calculator anymore, and just good habit just to write the answers, and if you can also highlight your answers so it's easier to understand what voltages or currents you got out of your node analysis. All right, now we're going to learn one more concept, the concept of supernode. And supernode is defined by the following. It's a voltage source that it's connected between two non-reference nodes. So every time that you look at an exercise and you see a voltage source that it's connected between two reference nodes, in this case V2 and V3, this is called a supernode, and the cool part is that you have a way to relate these two nodes together based on the voltage that you have on that voltage source. And this is just another way of getting an equation. If you took your node analysis and you are missing, or you are in lack of some equations and you need more equations, pay attention to your supernodes. You might be able to get another equation out of it. Now, I want you to pay attention here to another kind of special supernode. The definition says that it needs to be a voltage source connected between two non-reference nodes, but every time that you have a node or you have a voltage source connected between a node and a reference node, if you know the voltage of it, you actually know the voltage at that node, and you don't need to take the equations because you know that V1 is equal in this case to 10 volts. All right, so just couple of things to have in mind. Let's go over some practice problems so we can see these in action. And we'll start with this problem 3.3. And let's tackle and see how we solve it. As usual, let's go and design our circuit. And I do this a lot, again, so I can add things if I need, or redesign the circuit in a way that I'm familiar with, if there is like resistors in parallel or series or components that I cannot see what's going on. I always like to redesign this and put all the information that I can in the circuit. If I know resistance, if I know values of currents or voltages, I'll just include that right away into design. It helps me analyzing the circuit. And on this particular case, we do not have a reference node. We don't have the node voltages. So let's apply step number 1. And step number 1 states let's find those nodes and find a reference. So I'm going to pick a reference on the bottom. And I have a node over there, and this node is actually 14 volts. I have another node over here. This is going to be called, I'm going to call V1 and V2. And I have another node over there. All right, step 1 is it's done. Let's go over step number 2. Let's take the equations out of the circuit. All right, for that I need to assign some currents. Let's go back to the circuit and put some random currents. Again, don't overthink here, just put something. All right, perfect. And after that is done, let's go over now our KCLs at those nodes, at the non-reference nodes. So we have 2. We have KCL at V1. We have I1 going in. It's equal to I2 plus I3. Let's apply Ohm's law. And I2 is V1 over 3. Now I3, I don't know anything about it, so I'm going to just leave it as I3 for now. And once I'm stuck, if this happens, I'm actually just going to multiply everything by 4 in this particular case. And then rearrange the equation a little bit. All right, let's put that together. You get 7 over 3. And all right, so now that I'm here, just to make it easier here in terms of I3, I'm stuck. I'm going now to my KCL at V2. that might help me keep going. All right, so here we have I3 is equal to I plus I4. All right, let's keep I3 there, and I is going to be V2 over 2. And you can kind of see where this is going now, because I can now substitute these on the other equation. Just putting these together. All right. All right, so I have two equations that are related with I3, so I'm going to put them together. All right, V2. And rearrange the terms, and I'm multiplying everything by 12 just to make my equation a little bit easier to follow. So 7 V1 plus 8 V2 equals to my 42. All right, so I have one equation, and I use the two KCLs, and now this is where the supernode comes handy. If I have a supernode, which I do have, I can write an equation on that supernode, and that equation is going to be V2 minus V1 is equal to 6 volts. All right, that's my second equation. And that's the advantage of identifying supernodes. All right, and now I can start going over step number 3. And step number 3 is to solve those equations. And I'm going to write the matrix, those equations in a matrix form. So I'll have the matrix A, which is equal to 7, and then 8, and then minus 1 and 1. And B is going to be equal to 42 and 6. All right, I want to find my X, which is V1 and V2. And for this particular one, let's just see Cramer's rule in action. Remember that V1 is equal to V. So Cramer's rule. Cramer's rule, it's another way of finding answers for your linear equations. And it states that, in this case, V1 is going to be equal to the determinant of a special matrix A1 over the determinant of A. And V2 is going to be equal to the determinant of an A2 divided by A. So let's see the determinant, let's see the matrix A1. A1, all I'm doing is substituting V1 elements of A by my B matrix. And A2, it's the opposite. I substitute the V2 elements of my matrix A by the elements of B. And now I apply the determinant of that, and I get my answers. All right, so let's do that. A couple more steps than the previous one, and the matrix inversion. All right, I have 7 minus 1, 1. Let's find the determinant of that. All right, and I get 15, so I have my answers divided by 15. And now let's find the determinant of special matrix, the A1 and A2. So let's change that, and I substitute now by 42 and the other one by 6, and find the respective determinant, and I get minus 6, and I apply exactly the same thing now. Oh, before that, let's just calculate the final answer. I get minus 400 millivolts, and let's do now the second column with B, find the determinant of that. All right, and if I divide that by 15, I'm going to get 5.6 volts. All right, so I need to calculate I, and I is going to be V2 over 2, so I'm just dividing 5.6 by 2, and you get your 2.8 amps. I'm going to highlight the answer, and notice that this is exactly the same answer if you apply the matrix inversion. Our last exercise, it's another problem where we have now two supernodes. One is an independent voltage source, another one is a dependent voltage source. And let's see how to solve this exercise. All right, I'm going to design the circuit. I know that these might seem a little bit tedious, but sometimes it actually helps a lot by designing the circuit in a way that you understand what's going on. And it allows you also to put information that you know about the circuit. All right. We have the 25 volts. We have our dependent voltage source that depends on the current that flows through that 2 ohm resistor. Let's put the values here. All right. Same thing applies here. We need to apply we don't need to apply step number 1 because the exercise is already giving you the reference node and the node voltages. We go directly to step number 2, which means that I'm going to assign currents to the branches that they don't have currents yet. Put those plus and minus the way that you want. Same thing here. Doesn't matter the direction. All right, and let's start taking KCL. All right, KCL at V1, it's going to be equal to all those currents added together. So I plus I1 plus I2. I'm going to apply Ohm's law to the currents that I can. So V1 over 2 ohms. So I missed the 2 ohms over there. Let me just put it. All right. And then we have I1 is V1 minus V3 over 6. And my I2 for now stays like that. I'm going to multiply everything by 6. Again, it's just a good practice. If you do it, makes things easier. And put everything together. All right, and now I'm stuck here, and I can move to our KCL at V2. And that states that I have I2 equals to I3 minus I4, so I2 and I4 are entering the node. Let's apply Ohm's law to the ones that I can, and notice that I can find an equation that substitutes on my initial V1, KCL at V1. All right, let's do that. So that equation that I'm highlighting here, it's going to be put it there. And if I do that, I get the following answer. All right. Let's go over KCL at V3. And this one tells you that I1 is equal to I4 plus I5. Ohm's law to on the nodes that I can do that. And to make things easier, I'm going to multiply everything by 6. And if you do that, actually it's very convenient because that's 6 times I4 can be substituted on my first equation. All right, that's what I'm going to do. I'm going to substitute all that into this part over here. Just for consistency, let's just put that. All right, and let's see what we get. We get 4V1 minus V3 plus 1.5 V2. And now I just get the minus V1 plus 3V3 equals to 0. Way easier to manipulate this equation and less error prone. All right, let's put everything together. 3V1 and 1.5 V2 and 2V3. All right, cool. So I needed 3 KCL equations to get my one equation, and now I still have 3 unknowns and 1 equation. If I go and apply the supernode, because I have 2 supernodes, again they are surrounded by 2 non-reference nodes. So for the first supernode, which is related with a 25 volts, we have V1 minus V2 equals to 25 volts. And then for Supernode 2, which is my dependent voltage source, we have V3 minus V2 equals to 5I. And actually I, if you notice, is equal to V1 over 2. I can substitute that in my equation and I get something like this. All right, so here you go. I got my other two equations, and now I have three equations with three unknowns that I can find answers. And I'm going back to the matrix inversion, so let's represent my equations as a matrix. So this is my step number 3. And my matrix A is equal to 3, 1.5, 2. Then I have 1 minus 1, and then 0 on V3. And I'm actually going to rearrange this equation. I like it to put it in this fashion so I don't make mistakes and I don't forget terms. All right, so I get minus 2.5, sorry, 2.5, 1, and minus 1. All right, that's your A. And now B, it's just the result of those equations. So 0, 25, 0. And I'm going to do the inverse. So it's always important to write that X, so we know what variables are we trying to get. And let's now define that 3 by 3 matrix. I already have it there with some values. Let me put them again. I get the 1, minus 1, 0, 2.5, 1, and 1, 1 and minus 1. Perfect. Let's define B. I believe B is already good. Yep, 0, 25, 0. All right, cool. So let's just calculate it. I do the inverse. And my answer is the following. I remember that we're calculating V1, V2, and V3. The units are volts. I'm going to make things easier here. Now I'm just going to highlight the answers. And they relate with these variables over here.